A very good afternoon, one and all. I welcome you all for this session at the venue all day, all night. The topics under this session would be foundations and deep excavations. I would be coordinating this session. It's my pleasure to welcome our chair for this session, Dr. P. Hariprasad Reddy, Professor, Department of Civil Engineering, NIT Warangal. He's done his PhD from IISc Bangalore. His areas of research interests are geo-environmental engineering, solid waste management, water and wastewater treatments. I also take this opportunity to welcome our co-chair, Shabana, Assistant Vice President, Strata Geosynthetics. She's done her MTech in geotechnical engineering, and with her 23 years of vast experience in geosynthetics, she would be the co-chair for this session. Now I request our chair, Professor Hariprasad Reddy sir, to please preside.
Thank you, Vishwajit. Thank you, Vishwajit. Good afternoon, everyone. I welcome you all to this technical session on foundation and deep excavation. So here we have one invited speaker and around 7 contributing presentations are there, in which 5 authors have turned up so far. So if all the authors are here, then we'll be giving 8 minutes of time for the presentation and 2 minutes for discussion. So the theme speaker will be presenting for 15 minutes, and we can have a couple of questions after that. So without much delay, we'll start the session. Now I invite Professor Benson Sheng from National Cheng Sheng University, Taiwan. So he'll be presenting on impacts from consolidation caused by deep excavation in clays in Jakarta, Indonesia. So I briefly introduce the professor. Dr. Benson got his PhD from University of Bristol in the UK, and then moved to London to work for several large-scale infrastructure projects in both the UK and Taiwan. He went back to Taiwan in August 2003 to join the university. His main research activities are deep excavations and soft ground tunneling. Simultaneously, he is also involved in some underground and offshore wind projects as a technical consultant or advisor. Dr. Sheng is a well-qualified British chartered civil engineer. He is the chair of ASRTC 6, as well as a member of TC 204 and TC 305 of ISSMG. Currently working for the Department of Civil Engineering of National Cheng Sheng University in Taichung, Taiwan. So I welcome you, sir.
Thank you. Yeah, yes. This one. Yeah.
Light change and point.
Okay. Yeah. Thanks for the chairman's introduction. And this is my 5th time to India, and first time in Goa. And I think it's an honor for me to be invited as an invited speaker to give a presentation today. And although today I'm going to talk about excavation in Jakarta, but I did work for Delhi Metro before. That's Delhi Metro Phase 2 underground package. Okay. So today my presentation topic is this one: the impact from the consolidation caused by deep excavation in clay in Jakarta, Indonesia. And I will recognize this paper as a follow-up of a journal paper which we published in 2023. And I will have 4 parts of my presentation. The first part is about the introduction, and the second part is talking about the FE modeling which we used, and then will be the result and the discussion. And last hour we will make a short conclusion. Okay, talking about excavation, as I mentioned, I know if I don't use microphone, can you all hear me? Yes. Yeah. Okay. Yeah, that's good. Okay. Just like I mentioned here, for deep excavation, top-down method is a method which one of the methods quite popular to be used. But it demands a significant, use this one. Okay. Oh, okay. Yeah, because I prefer two hands.
It's a pocket.
Okay, sure.
It's in the pocket.
Okay.
And this in
So I should put this
the pocket.
in the pocket. Here?
There.
Oh, here.
Okay.
Yeah. Okay. For the top-down method, because we normally has to use RC slab as a horizontal support, so it take a longer time. So that's the reason why I talk about I say amount of time to construct the excavation because we need the RC slab as a horizontal support. And diagonal wall can experience a substantial deformation during the waiting period because the casting time is longer. So really, we may have more deformations of the D wall, and both consolidation and creep, so-called time-dependent behaviors, play a significant role in the phenomena. So that's the reason why we want to talk about the time-dependent behavior things. And previous research, for example, like in 2019, Harald and Professor O in 2020, and Lim in 2003, and Deng et al. 2023. They all talk about the time-dependent behavior caused by the deep excavation, and it also say, time-dependent could enhance more wall deformations there. And that's the reason why we intend to do some research about time-dependent behavior of the excavation in Jakarta is still limited. Because I will explain why we want to talk about excavation in Jakarta later on. But as far as we know, the study for that is very limited. And that's the previous study I talked about, the paper which we published in a journal in 2023. We use 3D FEM analysis. Actually, that's places use Jakarta as a background, and also we use a model which you can consider time-dependent behavior, like the soft soil or even soft soil creep, in order to understand what happens, for the deformation caused by the top-down excavation. And it is suggested the soil parameter obtained from the lab calibration were not significantly reliable. I will explain that in my next two slides. And lack of dependent result from the construction test introduced the major the uncertainty because we don't have a reliable SI data, so it has uncertainties for the effect of time dependent. So that's a background for us why we want to do this study and try to get some conclusions. Okay, now talking about the uncertainty of the soils, which we have here. This is a figure which we have, because we use the underground work in Jakarta MRT excavation as a background. As you can see, these assays show the undulation strength, and these assays show the SPDN value. This shows the SPDN value. And you can see the data actually quite scattered there. So you even cannot have a kind of relationship between the SU and the SPDN value. And we try to explore why, because supposedly if you understand from the statement made by Professor Skemter, it should have. So we look at the data which we have, the so-called SQD, sample quality destination, recommended by Professor Tazaki and Professor Pak, to evaluate so-called sample qualities. And in fact, by the volumetric strength which you have from the sample, you understand in the most of the samples which we have are in level C, D, E. But actually, Professor Tazaki and Pak say, if you want to do the undisturbed sample, you need to keep level in A and B. So that's one of the reasons why I say, maybe our test data is not that reliable. So, and again, if you look at this is a sampler, a thin wall sampler. Suppose the tap here should be rounded, but as you can see, that's totally twisted. And let's they use that to do the sampling work. So from these two, we understand, say, our sample are kind of disturbed. So and also we look at the CPD result and understand actually say deeper than like maybe 8 meters below surface ground level, the soil actually quite stiff. So this gives us a kind of confidence, say, oh, we have to do more tests together with CPD to get more reliable test data. That's what the site condition have. And very special thing is, even though that's in Jakarta, funded by Japanese government, but we, as a company or engineers from Taiwan, we have a chance to be involved in this project. So that's the reason why when we have the first tunnel breakthrough, we have our national flag there. Okay. Here comes to the last page of my presentation. So that's some conclusion which we got here, because we do find some sand layers between very thick clay. So that's the reason why we have a need to evaluate what the consolidation and even the creep, affect the deformations. And we in fact, we understand from the simulation which we have, we did point out, say, consolidation actually is quite an important factors, for the deep excavation in Jakarta using the top-down method. But as I just mentioned, we do have some uncertainties about no matter the time-dependent soil parameters like a compression index or even the swaying index or like the creep index, and even the construction time of the slab. So we want to explore, those parameters individually one by one. So here talking about the FE models which we have here. We use software process and do the two-dimensional analysis, and that's the case. That's a profile excavation profile together with the soil which we have here, and as you can see, that's excavation down to like a 24 something below surface level, but the wall actually is not that deep. It's up to 33 meters, because as I just mentioned, going down, further down to 8 meters below surface level, the soil is quite stiff. And the same excavation profile we use for the 2023, so that's the reason why I say that's a follow-up. And we did have embankments nearby, so we have to consider what the impact from the consolidation. Okay, so very quickly further explain the FE models which we have. So we again use soft soil creep models. But just like I mentioned, in SSC, here lists all the parameters which you have to use there. And just like I mentioned, the consolidation parameters here, what we include have the compression index and even the swaying index, and also the creep index, and we use a uniform very fine mesh in our analysis, and a value of 0.7 we use for the R-inter, and this is the construction phase which we assume in our analysis, and that's the structural parameters basically used for the retaining wall and also for the RC slab in our model. Okay, now we want to explore the parameters one by one. Sorry, how much time I have now? Another 5 minutes, okay. So I have to be quick. Okay, so we want to explore the parameters one by one. Okay, so the first one we evaluate is the so-called compression index. So if you look at the result here, this is a ratio show you what the maximum wall deflection is divided by the h. Okay, and here we try to change the compression index there. So as you can see there, actually the line here is quite straight, quite flat. So it means the compression index may not give once you change the compression index, may not give you a very significant change for the wall deformations. So it means even though we don't have a confidence about the compression index, it should be fine because it doesn't change a lot. So that's the first conclusions which we have from the compression index. And second one is about we talk about the swaying index. Okay, y-axis is the same with the compression index, and here we change to R bar. Yes, that's a swaying index. But you can see swaying index actually give more changes. If you have different values of the swaying index. So looks like the uncertainty of swaying index can lead a more significant change of the maximum wall displacement, which we based on our testing. So that's what we have for the second parametric study. And the last one is about the creep index. Again, we try to put in the figures here. So the same ratio, I mean the maximum wall displacement divided by the excavation, and that's the creep index. And in fact, if you have a creep index less than 0.012, and that's no significant change there. But once you have a value more than that, and then it will affect more. So for this index, I think we will need more explorations. I mean, to confirm what the value will be. I mean, by like a laboratory testing to understand what the creep index will be. And the last one is the construction time. So our understanding is the construction time. If you have some time longer, indeed, I mean, you are going to have more displacement rather than the original one. So construction time really is the issue. So here I come to the conclusion. Very quick, just like I say, the compression index doesn't significantly affect the result, but shredding index it does affect a lot. It does affect a lot. So really, you will have to consider what the real shredding, get the more reliable one. And the creep index, as I just mentioned, as long as you have a value more than 0.012, and it is going to affect more. So more reliable testing about the creep has to be done, and also the construction time is also an issue to affect the maximum wall displacement. Okay, that's the end of my presentation. Thank you very much. Yeah.
Having any questions, you can ask to the speaker. Yes.
Thank you, Professor Benson.
Thank you.
I was just wondering, when you simulate the wall deformation, how did the pore pressure work? Because it's saturated, right?
Yeah.
And you're talking about consolidation.
Yeah,
so
yeah.
How was the pore pressure response?
We actually, I think we actually let me think about, because we actually try to compare the pore pressure and I think we do have a kind of during the consolidation time we do have a kind of dissipation of the pore pressure.
Yes.
Yeah.
At the same time, as evident from your results, since this is an unloading problem, correct? So we really, to start with, we don't expect CC to make much of a difference. And that way, the more than consolidation, it's kind of a swelling or like expansive unloading behavior. So I was just wondering, did you notice any negative generation of excess pore pressure, or like which way was it dissipating? Was it more of a consolidation or deformation problem, or a flow problem when water is coming out, a seepage problem?
Well, okay. I think that's a very good question. Because in fact, in this paper, we actually pay more attention about the wall deformation instead of pore pressure. Yeah, because the issue is we don't have the piezometers. What we have is only the observation well. So really, you cannot get it what the real pore pressure will be. But by the papers we published in 2023, we think consolidation play a more critical role rather than creep, because based on the portion of the consolidation which we have from the analysis. So what I can tell you is that based on our analytical result, we can tell you is consolidation may play more critical role, because it is about like almost 30% of the deformation, the total deformations. But in reality, I think we still need to explore more later on. Yeah, thank you.
Thank you.
Thank you,
Professor.
Yeah.
Any more questions? So if no more questions, I thank the speaker,
Thank you.
Professor Benson,
Thank
for
you. Thank you very
taking
much.
the time.
Thank you.
So, as a token of
request-
appreciation,
Yeah.
so we request you to take them.
Yeah. Thank you. Yeah. So can you use? Thank you very much. Thank you.
The speaker is busy with another meeting. I think he's leaving. So we'll continue the session.
Sorry, because I need to join the council meeting, annual council meeting. So thank you very much. Thank you.
So now I hand over the session to our co-chair to continue the proceedings.
Thank you, sir. Good afternoon, everyone. Let's call for our first presenter, Assessment of Gravel Soils in Bridge Foundation Construction using X-rays, CT analysis, and density log. I would like request author to come and present. Thank you.
I request to take 7 to 8 minutes for presentation.
Yes, okay. My name is Kota Wakinaka from National Institute of Technology Kumamoto College in Japan, and I'm going to have a presentation on this topic. And this is contents of my presentation. And first of all, introduction and research background. And in Japan, the standard penetration test is recognized as the representative investigation method. However, since the test is conducted at 1 meter intervals, so it is difficult to identify localized weak soil zones. Furthermore, relying on N values to derive various soil properties for structural design is inappropriate. So this study aimed to identify bearing stratum prior to bridge foundation construction using N-various X-ray CT analysis of boring cores and density log. X-ray CT analysis was used to estimate core density, and the accuracy of the density values was assessed with density log results. Based on density, we attempt to evaluate the bearing stratum, and the results are reported here. And next, survey site and survey method. This study area includes river bridge located within Kumamoto Prefecture, Japan, and the stratigraphic composition is shown in this table. The fourth layer is the bearing stratum, and consisting of a sandy gravel layer with cobbles, showing N values greater than 50. However, in the upper part, a slightly loose gravel layer is distributed. Therefore, careful attention is required to accurately identify the bearing strata. And next, survey method. In this investigation, we attempt to reliably identify irregular soft zones within the bearing stratum using X-ray CT analysis and density log. Observations of boring cores shows that the gravel content on the core surface does not always correspond to the interior. Therefore, X-ray CT images were used to visualize the interior of the cores. Furthermore, CT values were used with the aim of countability representing the visualized core interior. CT image always was performed on slices at 1 centimeter intervals, and the average CT value within each cross-section was calculated. The CT value were converted to electron density using a correlation based on actual density test results. In addition, the conversion from electron density to physical density was calculated from this formula by Electra company. And next, survey results. This figure shows the depth distribution of density values obtained from X-ray CT and the density log. The terrace deposit layer, which serves as the bearing stratum, has been identified from depth of 30.82 meter from here. So these are shown terrace depository areas. And although there is generally a strong correlation between the densities obtained from X-ray CT analysis and the density log, some localized deviations are present with the density log tending to show lower values. This is particularly evident in the upper terrace deposit within this section. This discrepancy is considered to be largely influenced by the lack of close contact between the casing pipes and the borehole ore. We conducted the density log with the casing pipes. However, when the gravel is small or the substrate is rude, the gravel moves easily and cannot be excavated properly. In such cases, a void is formed between the casing pipe and the borehole wall due to the irregularities of the borehole wall. On the other hand, the densities between these depths exhibit a strong correlation trend. We have confirmed from the observation of the borehole core that it is a clay layer. So, of course, no gravel. It is considered that there was little no gap between the casing pipe and the borehole wall. As a result, the correlation with density exhibits a clear trend. This can also be considered supporting data for the hypothesis that the density discrepancy is due to a lack of close contact between the casing perimeter and the borehole. And next, this figure shows N values at two representative locations and the evaluation of the bearing stratum. For number 2, since the N value remains below 50, even within the terrace deposit layer, the bearing stratum is evaluated from 34 meters. For number 1, the N value reaches 50 immediately upon the entering the terrace deposit layer, indicating that based solely on the N value, the upper part of the terrace deposit layer can be considered suitable as the bearing stratum. However, number 1 corresponds to the location where the density values were previously shown, and the upper part above the measured density may consist of small gravel or looser matrix. Therefore, since the upper part may be loose due to redeposition, the bearing stratum is evaluated at the depths near 32.2 meter, where the discrepancy between the two density values becomes very minimal. And next, I will discuss the correlation between the density values obtained from X-ray CT analysis and the converted N values. In the terrace deposit layer, which serves as the bearing stratum, the converted N value exceeds 50, whereas in the former riverbed deposits, it remains below 50. It generally shows a tendency for N values to exceed 50 when the density is greater than approximately 2.3, suggesting that density can serve as one of the indicators for evaluating the bearing stratum. And last conclusion, we conducted the bearing stratum evaluation not only based on N value, but also using X-ray CT analysis and density log, with the aim of relatively identifying the bearing stratum. As a result, these conclusions were obtained. Thank you. Thank you for your attention.
Thank you so much. Any questions? No questions? Thank you so much.
Okay, thank you. Thank you so much.
Our next topic is thermal performance of a geothermal pile group in the presence of coupled thermo-hydroflow condition in layered soil. Mr. Arvind Kumar.
This one, right?
So good afternoon, everyone. So I'm going to present thermal performance of geothermal pile in a group and presence of coupled tiers flow condition in layered ground. So I'm using my current designation, but most of these works were done during my PhD at IIT Bombay with Professor Prasenjit Basu. So it's there. So if we talk about geothermal energy, most of the time we think that a deep geothermal energy where temperature goes beyond 100 degree and we produce electricity. But when we talk about shallow geothermal energy, it's mostly on the upper layer of the soil up to 300 to 400 meter, and then temperature is almost constant after 5 to 6 meter depending on the geographical location. And we can utilize these potentials because when we change the weather, we see that in summer and winter temperature on the surface very, very differently. But beneath our feet, it's constant. We can utilize this potential to heat or cool our building depending on our demand. And that's the part of this research. So why we choose shallow geothermal energy over conventional heating and cooling method? Because we see that we already in this building in a cool environment and it's running on the air source heat pump most probably. So why we need shallow geothermal energy? It's because it's very sustainable, it's economical, and it's energy efficient. We call it renewable energy, so we are not burning our coal or not utilizing low efficiency electricity demand, so we can save a lot when we utilize shallow geothermal energy, and that's why it is important to investigate this topic. And it's not that it's happening for the first time because it's using from 1950, but thoroughly over the research, we investigate this topic, and then we have come to a more refining technology so we can improve its coefficient of performance even further. So if we talk about the heat transfer in the soil, because it's not a very core topic to the geotechnical engineering, so it's important to discuss. So we have 4 important mode of the heat transfer. Start with the conduction, advection, that heat transfers with the flow of any media like groundwater flow. And then we have convection, where heat transfers within the fluid itself because of the temperature gradient, and radiation, that is not much important of the geotechnical engineering. So how does this process influence the soil? If we discuss, we have on the coarse grained soil, consider either pebble or coarse grained sand, and how does heat transfer influence in coarse grained soil? That if you have very high hydraulic conductivity, it will be a drained process and it will change the thermal property of the soil. In terms of fine grained soil, it's not having a high hydraulic conductivity, very low hydraulic conductivity. So when we increase the temperature of the fine grained soil, what we will do that it will generate pore water pressure. Because if we heat the pore pressure, a pore fluid, it will try to expand. And if try to expand and there is no space to get out that water, then it will try to generate the pore water pressure. Once pore water pressure is generated, what will happen that it will try to dissipate over the time, and then until it's not dissipated, you get the undrained response, and once it is dissipated, you get the thermal consolidation and then deformation. So this whole process, it have 3 major components when it comes to geotechnical engineering: that thermal, hydraulic, and mechanical. When we talk about the deep foundation and where there is temperature is involved, we have to investigate this THM that we call famously thermo-hydromechanical coupling that influence the pile capacity and then soil-pile interaction on the surface. But for this presentation, I will mostly focus on the thermo-hydro coupling, that how temperature and hydraulic component is going to influence the process. So if we talk about a little bit mathematics here we see that the standard heat transfer equation in a porous media, where we have heat storage component, where we have fluid flow component, and then how heat transfer happens because of the thermal conductivity. And this is a Brinkmann equation. I am not going to detail of this equation, but how these 2 equations are coupled to effect of the thermal and hydraulic both. So if we look at here is a time dependent change in the temperature, del T over del T. And then because we have a thermal gradient here, what happens that density of the pore fluid changes in the medium. And that density driven flow creates a force, a volume force in a media, in a fluid, and that triggers a velocity here. Now once this velocity is triggered, what will happen that this velocity will activate this component. So by two-way coupling, the heat transfer and fluid flow both influence each other, and this process becomes a highly, you can say, non-linear process. So as we discussed earlier here, we can see the plot that how temperature changes in the ground over the summer or winter throughout the season and after a couple of days. So this depends on season to place to place, and after approximately 5 to 8 meters, it's almost constant. On the surface, there is a large temperature variation, and we can utilize this potential. In summer, we can extract heat from the building, send into the ground, so we can cool our building like we are seeing here. In winter, it's exactly opposite. So when environment is at the colder temperature, we can extract heat from the ground and then heat our building. That's how we utilize halogeo-thermal energy. And in terms of energy pile, why energy pile? Because for this, anyway, to sustain a building structure, we are installing pile. We can install geothermal heat exchanger in the pile and then utilize this process without any additional cost of borehole or any other medium. So when we install geothermal pile, the geothermal heat exchangers can be of a many shape and size depending on the pile diameter and need. So it can be a single U-loop here, as I explained. It can be double U-loop. It can be a multiple U-loop depending on the diameter of the pile. If it is a very big diameter like 1 meter, 2 meter, we can have 3 or 4 loop. Depending on the design, it can be coaxial as well, where you send the fluid from the center and then take it from the up. And when we want to install a large amount of the loop, we use a helical tube as well. So depending on the design, this may vary. Now, for this study, we took an example of 3 piles group at different spacing, and then there was a clay layer and a sand layer, and then sand layer is of course having high hydraulic conductivity. So we thought that how the natural convection process is going to affect the entire heat transfer process in this medium. We use finite element software for this design, and here we can see that the influence here, that how it affects that. In the sand layer, heat transfer is happening very fast compared to the clay layer. So initially, when natural convection is not triggered, you can see that the process is almost same in the both in initial portion now, but as time process, what happens that in the sand layer, you have a very high thermal expansion. And when we look at heat transfer or thermal temperature contour, when we consider only conduction, when we are not considering the coupling of thermomechanical process, thermohydro process, TH process, then we see that temperature is evenly distributed in both the layer, because we are not considering the hydraulic component. But when we consider the hydraulic component, here we see that in the sand layer, temperature is very narrowly, because most of the temperatures are getting dissipated far away because of the natural convection. But in case of conduction, all the temperatures are close to pi.
We have 2 minutes, Arvind.
Okay. And then when we investigated the heat storage capacity, we can see that the process of coupled flow is always enabled to store more energy depending on the pile spacing. Mostly in a group, we have pile at a small space, and we can see that when the space is 2.5 D, and in case of 3 active piles, we can store almost 60% more heat in that, or in terms of extraction, it will be the same. So if we compare the whole group system, that how the process is happening, that if we have just 2 active pile or 3 active pile at different spacing, and we compare with a single pile, we can see that in terms of conduction and natural convection for the single pile, this is 10.17%. But in terms of 3 pile, and especially as the close spacing pile, this increased to 30%. So this shows that when we model it with the proper physics that is happening in the ground, we can extract more and more amount of energy. So with that, we conclude that natural convection do influence the heat transfer process, and it affects our energy extraction and energy injection capacity. So when we design our geothermal pile, we should not design based on just conduction, because then we assume that the entire pile is increasing with the same temperature. But we saw that in process, it's not happening. When we have a layer of coarse grained soil where our hydraulic conductivity is more, we see that temperature increase is less, and this temperature difference between the section of the pile will influence the pile integrity and its bearing capacity of the pile as well. So we have to be very careful when we design with the different layer of the soil. So thank you, that's all from me.
Very nice presentation.
Thank you very much.
Anyone, any questions?
Yeah, what is the temperatures that you are talking here?
So here we consider the ground temperature is 22 degree, and then the inlet temperature was 40 degree.
Okay.
So it was mostly simulating the Indian condition that we have a hot summer and we want to cool the building. So we take inlet as the high temperature we take from the building, and then ground, because ground is at lower temperature, 22 degree, the heat we get is lower than the 40, and we utilize this to cool the building.
Okay.
In winter it will be exactly opposite.
So this is basically numerical study, or you have any
This is the
field data you are...
This is the numerical study, but now where I am doing my postdoc, where we are doing in the field as well.
Okay. Thank you.
Thank you very much.
Anywhere we are doing it in real life project, these things in
Yeah,
India.
yes, we are doing it real life. I believe that we always talk with professors that why we are not doing in India. We are doing it in Europe, we are doing in China, we are doing in Australia, USA, almost everywhere except India.
Thank you so much.
Thank you very much.
We'll go for the next topic, non-destructive evaluation for the integrity of geostructures based on electromagnetic waves. Is not here? Okay. Later. Okay, sir. So we'll go for the next one, forensic geotechnical analysis of sinking of large concrete slurry tank.
I am here to present my paper, Forensic Geotechnical Analysis of Sinking of Large Concrete Slurry Tanks. Coming to the introduction, forensic geotechnical engineering deals with the reasons for non-compliance performance of constructed facilities. It analyzes the contributory and triggering factors that may have led to the undesired incident. Now, coming to the problem, we have two slurry storage tanks that were constructed in 2021. It is 15-meter internal diameter and 15-meter in height. The clear distance between these two tanks was 1.3 meter, and the tank walls were 1 meter thick, made of concrete. Both these slurry tanks are continuously sinking since commission. So the total and differential settlement in 12 months, the tank 1 has settled by 628 mm with a tilt recorded 1 in 30, and tank 2 by 734 mm with a tilt of 1 in 20. And the allowable limit of differential settlement is 1 in 500 as per IS 1904 2021. So these tilts are very high. So this was the tank that was tilting, and this was a plumb bob arrangement to measure the tilt of this tank. Now coming to the soil underneath, it has got a top fill material. It was followed by a thick layer of greyish soft clay soil. Beneath the clay strata, there existed moderately weathered to slightly weathered amygdoidal basalt rock. However, few boreholes drilled near the concerned location showed the presence of highly weathered and fragmented rock as well. Coming to the foundation details, the proposed foundation actually consisted of a pile group connected to a raft, which acted as the base for the slurry storage tank. Each tank was supported by a group of 97 piles in circular pattern, and diameter of these piles was 0.6 meter with a center-to-center radial spacing that varied from 1.5 to 2 meters. So this was the arrangement of piles, the 97 piles in concentric circular pattern, and minimum spacing was around 2.5 D, and the embedment length of the piles varied from 21.2 meters to 25.2 meters depending upon the availability of competent rock strata, and all the piles were socketed to a depth of about 1.2 meter. That's about 2 times the pile dia, 0.6 meter. Coming to the numerical investigation that was done to perform this forensic analysis, it was done in Plaxis 3D, latest version. The soil stratigraphy was divided into 3 layers. So we have the top fill material from 0 to 1.5 meter, and then soft clay soil from 1.5 to 22 meter, and then medium gray basalt rock that was extended to 30 meters. The constitutive model for the fill and rock layer was Moore Coulomb model, and soft soil model was used to represent the behavior of the sandwich clay layer, which was exhibiting a high degree of compressibility. In fact, the compression index was around 2.37, and pile group was modeled using an array of elastic embedded beams. Maximum value of the skin friction resistance and base resistance has been entered as a part of embedded beam property. Now the raft was modeled as an elastic plate with a thickness of 3 meter and modulus of velocity of 30 gigapascal, which is a value for the concrete. And connection between the pile and the raft was set to rigid in the present investigation. And the total static load that was coming, including the self-weight and the weight of the filled slurry, was around 6,689 tons. And if we calculate the surface load intensity, dividing it with the area, it will come around 289 kilopascal. So this is the finite element model in structures mode, where just you can see the raft and the connected piles, 97 piles, and the superimposed load of 289 kilopascal. So these were the properties of the soil: filled up soil, grace clay soil, and basalt rock. And we can see for the clay soil, it had a cohesion of 40 kilopascals and friction angle of 3 degrees for a huge thickness. Now coming to the results and discussion, if you see the effect of rock quality condition, the average of RQD and core recovery was around 70%. Now if we calculate the ultimate bearing capacity of this rock socketed pile based on IRC 78/2014, it will come around 4,483 kilonewton. Sorry, it is kilonewton. And however, in few boreholes located closer to the tank area, the rock quality designation and the core recovery values are very low. In fact, RQD plus core recovery by 2 will come less than 30%. In such a case of fragmented rock material, based on IRC 78/2014, the magnitude of ultimate bearing capacity was obtained just as 2,912 kilonewton. So, from the current numerical investigation, we have found that the maximum axial force developed at the pile base is around 780 kilonewton. So based on that, we can understand that the factor of safety was around 5.7 initially, but if poor rock quality conditions existed at the pile base, it would have reduced to 2.4. Now coming to the effect of downward drag forces. So for this, the numerical analysis was conducted with a consolidation calculation, where the soft layer was allowed to consolidate for a period of 365 days. Axial force at the pile tip was found to increase from 780 kilonewton to 996 kilonewton. And this would affect the factor of safety. The factor of safety would go down now from 5.7 to 4.5 in case there is a good quality rock. But in case if the rock quality was much lesser, as RQD and core recovery by 2 is less than 30, as was the case in some boreholes, it would come as low as 1.9, considering the combined effect of downward drag and the existence of very poor rock condition. Although the failure risk may be substantiated with a highly reduced factor of safety, it does not explain the cause of failure, because still the factor of safety is greater than 1, and the settlements were around 50 to 60 mm only. Now, another possibility could be that the pile is terminated on soft clay. High magnitude of total and differential settlement may not occur even if pile was terminated in very weak fragmented rock zone. In this scenario, it is suspected that the pile was terminated in a much softer material with comparatively lower stiffness and strength. Distinction between the rock and the soil at the site was just based on specific gravity. In fact, something greater than 2.7 was classified as rock. However, specific gravity is not a proper indicator of the strength. Hence, a numerical investigation was conducted by extending the soft clay layer to 30 meters. Hence, the simulation represented the case of a floating pile surrounded by a consolidating soft clay layer. Now, results from the consolidation analysis revealed the total and differential settlement of the pile raft foundation. The maximum settlement and minimum were around 701 mm and 471 mm. This was very close to the maximum settlement observed at the site, which was around 628 mm and 734 mm. However, the tilt obtained in the present analysis is about 1 in 80. This was much lesser than the reported value of 1 in 20 and 1 in 30. This may be attributed to the very rigid connection that was assumed in the FE model between the pile and the raft. Also, the raft-soil interaction was not modeled accurately in the analysis, as it may be concluded that there is a high probability that most of the piles are founded on soft compressible clay strata. Finally so this is the picture finally where you can see the deformed mesh, and due to the consolidation and due to the overlapping of the pressure bulb, this is the way the tank was getting subsided. Coming to the conclusions, presence of a highly weathered and fragmented rock deposit reduces the factor of safety drastically from 5.7 to 2.4, and the downward drag on the pile is found to reduce factor of safety further from 5.7 and 2.4 to 4.5 and 1.9 respectively, considering the moderately weathered and highly fragmented rock deposits. And the analysis also reveals that there is a high probability of piles being terminated on soft compressible clay strata, leading to heavy settlements. That's all from me. Thank you.
Any questions?
So, thank you for the presentation. Water table where you have considered?
It was 1 meter below the ground level.
1 meter below?
Yes. It was actually, the site was near Mumbai region only.
Okay.
So they told me the details were given. Pretty But we didn't have the SPT N value under the proposed site. It was a large area. They had many boreholes, SPT values were given. So it was given 1 meter below the ground level. So I had considered like that.
But your raft thickness was 3 meter, no?
Raft was?
Pile cap thickness.
Pile cap thickness was, it was, the tank wall was 1 meter. Pile raft thickness was 2 meter.
Mentioned 3 meter. So
Okay, maybe 2.
pile and pile cap both are floating. You have taken floating pole.
Means you are asking there is 0 to 1.5 meter, there is a fill material. Below
Yes,
that
okay.
only.
Okay,
Below
thank you.
that there is a thick clay layer.
What is the proposed solution? Now now it is settling, right?
And this may be a problem of inadequate soil investigation only, but we could have done some sleeving on the piles to reduce the negative skin friction in case if it was due to negative skin friction. Sleeving on the pile to reduce this negative skin friction issues.
Instead of socket of 1.2 meter,
Oh,
there was a socket of 1.2 meter for the piling of what you have shown there. But I am little bit surprised that you're telling there was a soft soil, and then when the adjacent bore log was having some weathered rock, right? And because of that, all these kind of an axial forces have increased on the pile. Because the pile is 97, it's a huge amount. And the depth is huge, like 22 meter.
Yes, 22.
And then you have a socket properly.
1.2 meter. Yes.
so there
That
may
is
be-
why I'm not getting any issues if it is properly installed on rock. But I don't think it is but the settlements are coming only 50-60 mm. In fact, even after reducing the stiffness of the rock to very low level, I considered poor quality rock also. But still, such settlements are not coming.
So we could actually attribute this entire thing is that it was not properly embedded in the rock. That's the major issues.
Yes.
And
How
that
they
led
ensured it at the site has to be checked, because we don't have proper. Only thing they told is it was based on specific gravity that they distinguish between rock and soil.
that would lead to such a huge settlement and such a huge inclination. 2.7.
Yeah, because the clay layer, if that is still soft at that level, it will be. Because maybe in most cases, it may increase, definitely.
Yeah, some case, I would say. Thank you so much. Very nice information. Thank you. So, our next presentation is effect of footing, soil stiffness ratio with axial dynamics of shallow footing. Mr. Bipin Kumar.
Yeah. So I'm going to talk about this particular paper, effect on footing soil stiffness ratio on axial dynamics of shallow foundations. So there are a couple of authors, me and my student. So you see that there is a figure over here, and you have a footing which is usually shallow, and shallow footings have a slenderness ratio of 0.2522 LP by RP. LP is the length and RP is the radius of the footing. And the footing is embedded in a soil, and the soil is resting on a rigid bedrock or a rigid stratum. So when is this problem necessary? So you see that you have a compressor compressor over here, which is basically a reciprocating machine. You have a rotary machine, which is a rotary compressor, and you have an impact machine, which is a forging hammer. So all these kinds of machine need a footing or a foundation to rest on, and when these machines operate, they generate dynamic loads. Okay, and these dynamic loads have a wide range of frequencies varying from low to high. So this particular problem that we are going to solve or that we are going to develop is basically for these sets of application. So what are the formulations that are still available in the literature? Okay, this is a pretty old problem, but there are quite a lot of formulations already available. So you see that there are simplified analysis, plane strain analysis, which is basically a Winkler type analysis. Then there is this cone-based formulation, which again is based on 1D wave propagation theory. And then there is this lump parameter model where you basically calibrate field data to fit in with some inputs for your theory that you have. So there are quite a few authors that have contributed to these particular kind of analysis. Then there is this rigorous boundary element type formulation, which is also there in the literature, quite old. And finite element analysis is always there, but for this kind of problem, there is only one literature that I could locate. So this is by Kaushal and Usima. So all these formulations that you see, they have certain deficiencies. Some of them are based on simplified theories, not rigorous enough. It does not incorporate three-dimensional effect. And they might be based on complex mathematical schemes. You are pretty much aware of finite element analysis. Boundary element formulations, we end up using a software and all. Otherwise, when we are talking about these foundations for these kinds of problems, there is another issue that people have not really investigated or not talked about. These studies consider the footing to be completely rigid. They do not incorporate the effect of stiffness of the footing. So we have developed an analysis, and through that analysis, we have tried to investigate whether the stiffness of footing is actually necessary or not. So you see that I have the same problem. This is my problem statement. I have a footing which has an input of Young's modulus of the footing. And then because this is a dynamic problem, so I have this density as well. This footing has a radius RP and has a length LP. And the base of the footing to the top of the, or to the base of the soil layer is basically H. The soil is basically homogeneous. This is a soil stratum. If you look into the literature, this is usually defined as a soil stratum when a soil is resting on a rigid bedrock. So there are few properties associated with the soil as well. The first thing that we do is basically we have an applied load, axial load, and we consider a r theta z coordinate system to solve the problem. The first thing that we usually do is consider a displacement field for the soil, which is given by this particular equation. And in this particular equation, you see that uz is the displacement of the soil, which is equal to w multiplied by phi. W is basically the displacement of the pile or of the footing in the vertical direction, and phi is basically the soil displacement function. So we begin with this assumption of the soil displacement field. Next, what we do, we take this entire problem and apply the extended Hamilton's principle, which is basically nothing but a dynamics part of the virtual work principle. Okay, so in this equation, you see that there are parameters k, pi, and WNC. K is basically the kinetic energy of this entire system. Pi is the potential energy of this entire system, and WNC is basically the work done by the external force that you're applying. So these are the equations that you see. So in K, this particular first term is the kinetic energy of the footing itself, and these two terms are the kinetic energy of the soil. In the second equation, the first term is the potential energy of the footing, which is not considered in the previous analysis, and these two equations that you see, the potential energy of the soil. And this is obviously the work done by the applied external force. And all these equations are actually expressed in terms of this particular displacement field. And obviously you're using the theory of elasticity, which is used in any continuum mechanics work, or elasticity theory. So we put all these equations in this particular equation, and then we apply the necessary mathematics, or do the necessary mathematics, variational principle. And we arrive at the differential equation for the soil, and we also arrive at the differential equation for this part of the soil domain, and then we arrive at the differential equation for the footing. Okay? So let's go back to the first differential equation. So this differential equation contains this particular parameter gamma, and gamma is basically describing the rate of decay of the soil displacement with increasing radial displacement, increasing radial distance from the footing interface. Okay? So now there is an analytical solution available, or it can be solved analytically. Otherwise, we have to do numerical solutions, which we usually avoid. Then you have a solution for this differential equation as well, for this part of the soil. And in this equation, you see that there are parameters Ks, Ts, and omega s, which basically are soil parameters. Ks is the compressive resistance, Ts is the shear resistance, and omega s is the inertial resistance of pile, of the soil. Obviously, Ks and Ts, there are two parameters associated, so it is better than plane strain, one cone-based model, and other lump parameter models where parameter fitting is required. Then you have a differential equation for the footing as well, and obviously it is also associated with this Ks, Ts, and omega s, but within its limits. So all these equations that you see, it can be solved analytically, and because you see that this Ks and the solution of this particular footing, which is given by W, they are interdependent. We write a MATLAB code there is an algorithm, an iterative algorithm, and we use it to obtain the solution to the particular problem. So you see that there are two figures over here, and in these two figures, this y-axis is basically the real part of the stiffness versus the dimensionless frequency, and this is the imaginary part of the stiffness, which is the versus the dimensionless frequency. And you can see that these two quantities are given in this particular equation, where these, if someone who is working in dynamics must be pretty familiar with this equation. So this Kv is nothing but the stiffness, which is very similar to the F equal to Kx equation. But this is, because this problem is dynamic, so you have dynamic quantities associated with it, and that's why you have frequency in the x direction. So we have validated our model with this particular finite element framework, and we have got a pretty good match for this particular problem that we have had. The amount of difference that we got for the static stiffness was about 6.5%. Okay, so we have solved quite a few problems, and there are some range of differences which could be somewhere around 15%. But it's not necessary that this particular method is completely perfect. So the thing that we wanted to investigate in this particular paper was basically the effect of footing soil stiffness ratio. And what we have done is we have this LP by RP 0.25, which is basically the footing slenderness ratio of 0.25, and we have EP by ES, which is basically the footing soil stiffness ratio. And we have obtained the results of the real part and the imaginary part of the stiffness and plotted it against the dimensionless frequency. And we have obtained the results for various values of EP by ES, which is basically the footing soil stiffness ratio or footing soil stiffness contrast. So you see that there is not a lot of difference when you keep on changing this EP by ES in the real part. The difference, if you compare with EP by ES 50 and EP by ES 2500, you will get around 7% of difference. Okay, so that is at the static level, but if you keep on increasing the frequency, the difference reduces for the real part. While for the imaginary part, if you look at this imaginary part, I have presented an exaggerated view, but you look at the axis, this is 4.8 and this is somewhere around 4.94. So there is not much of a difference. It is about 7%. So this is for LP by RP 0.25. Again, when I take an LP by RP 2, the footing slenderness ratio is about 2, which is a higher value. You see that again I get a certain amount of difference, and the footing soil stiffness ratio does affect the results. So assuming it to be completely rigid might not be valid. However, depending upon whatever your engineering requirement is, you would want to go for a better accuracy. So then you can incorporate the stiffness of the footing as well. So you have some results over here as well, similar results to the previous slide. And the another one important aspect that gets affected is basically this particular resonant frequency that you come across when you plot it against the frequency. So all these results are available. So the conclusion that we have drawn is basically we have developed an analytical model, which obviously is very accurate. Quite accurate, I should say, when I compare it with other finite element analysis as well, or other boundary element analysis. The method produces accurate response for shallow footings. The thing that we wanted to investigate in this particular paper, the analysis is employed to investigate the effect of footing soil stiffness ratio. It is found the effect of footing soil stiffness contrast, which is basically the footing soil stiffness ratio, can be incorporated in design for EP by ES less than 300. So if the ratio of the foundation footing stiffness, the footings Young's modulus and the soil Young's modulus is less than 300, then you can incorporate, or then you should incorporate the value of the Young's modulus of the footing as well while doing such an analysis. So this is the conclusion we have drawn from this particular study. In the literature, nothing is done for shallow footings with slenderness ratio from 0.25 to 2. So that's why this study was conducted, at least to quantify as to what is the amount of difference that you can have. So this was all from this particular presentation. Thank you. If you have any questions.
Thank you. Any questions? Anyone? Thank you.
Yeah, thanks.
We have a next paper on thermal assessment of geothermal micropiles as a sustainable heating cooling solution for existing buildings by Arvind Kumar.
So hello everyone again. So this I present from my postdoctoral work from NTNU Norway, that where we are doing some field study there, and there we investigated the micropile, because in earlier presentation we saw geothermal pile. So geothermal pile are mostly installed in a new buildings when we are pre-planning and constructing the buildings. But what to the buildings that is already constructed 30, 40, 50 years back, and we forgot, or we did not plan enough, or we did not think for the future, and we did not install the geothermal heat exchangers in those piles. And now, as we see that, if we see the building scenario in Europe, mostly where I work in Norway, we see that more than 40% on average buildings are 60 years or more than 60 years. And then if we consider the whole building, more than 90% buildings are more than 30 years, and then these geothermal heat exchangers are not installed in those buildings. So how to do retrofitting for those buildings, as we say, energy retrofitting. And if we see that, if we want to go into meet the Paris climate target by 2050, over 97% of the European buildings has to be energy retrofit, because in Europe, approximately, if we see 40% of the energy consumptions are in the building, because they require a lot of heating and cooling demand in Europe for the buildings. And if we see that 50% of the gas consumptions in Europe goes to heating of the building, and they are producing a lot of carbon dioxide. That's why in Europe we are trying to energy retrofit our existing buildings, and then that will be the only possible way to cut the CO2 footprint in the buildings. How to do that? If we see here, to meet the Paris target, we have to have at least 60% of the buildings sector to retrofit by 2030. That is, I assume that it's going to cross anyway, that will not be possible. So we have to target by either 35 or 40 to do so. And if we see how it is complicated, that how we cannot install energy piles, because if we see the scenario, this is you can say concrete network of a city. And at the many places we have a historical monument where we cannot change any design or any new construction to the upper structure. So how it is possible to energy retrofit this system? What we can do, that we install micropiles, and it's that micropile is not a new, that it has been used since Second World War, that to underpin the buildings and then provide additional support of the building post-construction period when we see a high deformation. Why we use energy micropile? Because the machine is very small and it can go into the basement and install the pile. It creates very less vibration and then very small diameter pile. For new building, it can go up to 300 mm, but for existing buildings, mostly it's in the range of 100 mm to 150 mm, and it can easily go into the basement and install the micropile. Depending on the design, the length can vary from 5 meter to even some buildings have used 50 meter, but that is very rarely in that case. And we utilize opportunity here that when we are doing the strengthening of this existing building, we can install loop in this energy micropiles itself. So further we can utilize this for the energy or heating and cooling of the building. So if we see the type of micropiles on the base of construction, so these are the older versions where we grout the micropile in a borehole, and then either it can be a gravity grout only, otherwise we can put packers at different spaces and then pressurize these boreholes to have a bigger, you can say, a different bulk in the pile. But recently there is a popular type is coming that we call type E self-drilling, where you have a reinforcement bar, I would say, that is centrally hollow. It has a drill bit, it just rotates, drills the hole and then grouts at the same time. And then we leave this central bar as a reinforcement there. So it's pretty fast process that you can install one micropile in 1 or 2 hours compared to these, they take much more time. So this is gaining more and more popularity in Europe. So this is one of the classical example in a Turku, Finland parking facility where they installed 2,000 micropiles where length were varying from 15 to 55 meter. And they installed U-loop as we discussed earlier in micropiles, and now they use this for de-icing of the surface and then heating and cooling of this adjacent building. And it's been working from last 5 to 7 years. It's installed in 2017 or 18 if I'm not wrong. But only thing to consider that they had to install these pile diameters little bigger because they used U-tube. In most of the buildings we have pile diameter quite small where we cannot install the U-loop. So here we are proposing a solution that generally what is that if pile diameter is big, you have a U-loop that can usually install. But what happens that most of these self-drilling piles are like this, where you have central reinforcement and this reinforcement is hollow from the center. So we come up with a solution that this type of separator's tubes comes in a market for the borehole. Why not we install this separator's tube inside this hollow portion to look it like this, and then we can utilize this pile as well as an energy micropile. Otherwise, there is no way to utilize these piles as energy micropiles. So we did some numerical simulation. I made a numerical idealization of this tube as a single tube where half is bifurcated and then half portion is used as inlet and then other half is used as outlet. So this is inlet of the fluid, this is outlet of the fluid. We wanted to compare that if we're doing thermal performance, then how much are these processes, how much giving more or less energy compared to the traditional U-loop. We did some numerical simulation and we see that indeed the separator's loop is giving around 15 to 20% lesser energy extraction or energy storage compared to the traditional U-loop. But the benefit of this that a lot of the micropiles in upcoming future are not going to be utilized as energy micropile because we cannot insert the U-loop in those piles because of the less diameter. But we install separator's loop, then what will happen that at least we can operate on 80% efficiency, and that will be much more useful because previously we saw that compared to the traditional heating and cooling systems, energy piles, geothermal energy is quite useful. So again, this is the U-loop and this is separators. We see that, and then we see that separators is, in terms of energy storage, it's around 50 watt, where separators is around 40 watt, so approximately 15 to 20% less. Why this is happening? Because if we see to the previous image, because of these arms, so this is known as shank space between inlet and outlet arms. Here it has a wide space, so there is no any thermal interaction between these two arms, at least not as much as in this, because in this thermal interaction is quite close because inlet and outlet loop are very together, stick together here. So that's the reason that in separator's loop we have thermal contours very close to each other and most of the heats are dumping close to the loop. That's the reason that it's giving less energy. So we took this to the field level as well, where we had installed 2 energy piles that we are monitoring that in Norway, and then we installed 6 micropiles in these locations. As we see that during the installation, we see this central reinforcement, a central hollow bar that goes inside, and once we grout that, it's look like that. And we have central space here. Then we insert loop, that we saw that loop, separator's loop inside the micropile, and once it is done, it's look like this. So here we were installing last year November when we saw temperature dipping to -5 and we were all soaked in water installing these piles. As we see, when we installed all 6 piles, it's look like this, where we use 2 type of loop, 4 separators loop and then 2 coaxial loop. In earlier PPT, I discussed that how the coaxials look like, where we have inlet and outlet in the same tube as well. And this is the team when we install, we take help of some consultant companies to install the micropile, and this is how the site is looking now. So right now, before coming to India, I started the operation, so operation is going on, and then very soon we will get some result out of it. As we see that, we concluded that energy micropile can be a very good solution for the energy retrofitting of already existing building if we want to improve the energy rating of the buildings. And then, though the separator's loop is giving 10 to 50% less energy, I would say extraction or consumption, it gives a wide range of opportunity to utilize this technology or this type of loop in buildings where the less diameter of the energy micropile is there. And then I believe that at NTNU, we are doing for the first time in a highly sensitive clay, so we will get some very good data for thermo-hydromechanical characterization as well, because the clay is completely saturated and very sensitive. So I believe, as we discussed earlier, that THM is very important for the energy or for the pile load capacity. So with this, I acknowledge the contribution of Professor Singh, and then Malaysia and Alexandro and our industrial partners, those supported in installation, and then Lake DSC who funded this project. Yes, thank you.
Thank you. Any questions? So you have something?
So you said micropiles are mainly meant for the existing buildings, right?
Yes, sir. Mostly we can use for new buildings as well if we don't want to go for a very big diameter piles. But mostly when it's actually in Europe, they use this extensively for the under supporting of the building. So suppose that after 30-40 years, they have a very chunk of old buildings that starts to settle. So once you see that building is settling, they go to the basement, install the micropiles to support the buildings.
But for new buildings, as you said, separator loop is not energy efficient, right, in storing.
So for the new building, so suppose that if we go here, let me take you here. So this is happening for the new building. So there are many places where you don't need very big piles. So there people go for micro piles as well for the new building as well. Now these piles cannot be utilized for energy piles because these piles diameter are small and then you cannot install a traditional U loop. So you are bound to have separate boreholes. Either you can have separate boreholes to have a shallow geothermal energy that will again consume that you have to have a borehole to dig a borehole, you have to spend the money, and then it will take another space as well for the borehole. But with this we can install loops in this pile itself.
So what is the material, the separator that you are using?
This separator is mostly with either PVB pile or SDP pile. So high density polyethylene.
So here it is, your heat is entering one side of the separator and then
yeah, so here we see that here two bifurcation is there.
Yeah.
So if I see numerical aggregation, so in the center of the pile, two bifurcation are there, and at the end, these are joined here. So if you look at here, this loop is jointed together.
Okay.
So water enters in a one way, and then exists in another way. So we get the proper loop in single pile itself.
Okay, thank you.
Thank you so much, Arvind. Thank you, everyone. We had a very good session, and Arvind has presented two papers and micropile in one was a energy pile and another was an energy micropile. One was for the new building, another one for existing building. So some of the good studies what we have heard from Arvind, and it's a very nice presentation what you are giving it to it. Another presentation which basically have given us some kind of a discrimination between X-ray CT analysis and density log when we are basically arriving the SPT value by bore logs and how the differentiation we can see from X-ray and CT analysis. That was also a very nice presentation. The sinking of large concrete slurry tank, something new what we have seen. It's really amazing study. I want to know the solutions what that's going to happen because it's a huge tank over here. And of course we have found a little bit of about the footing soil stiffness. The equation what sir has presented was something to learn for shallow foundation, and we found that there is one gap where dynamic analysis of shallow footing when the equipments are resting and giving some kind of a vibration, that analysis is not being taken care, and it's a good equation and can be taken it more ahead in terms of studies. Thank you everyone for hearing us. Any questions, anybody?
Yeah, and we thank the organizing committee as well as the coordinators for giving the opportunity to chair the session.
Before we conclude, I request Ravikiran Vaidya sir to please present a memento to our chair, Dr. Hariprasad. And I also request Sujan Kulkarni sir to please come forward to present a memento to our co-chair, Shabna ma'am. I request all the presenters and all the audience to please come forward to have a group photo so we can conclude the session. All of you can join, please.